So our first speaker is Teja Kothakonda from I guess from Cologne and Free University of Berlin. So he'll be talking about thermodynamic limitation erasure, information erasure with computational limits. So Teja, please take it away.
Thank you very much, Yang. I will. So I'll just start my slides now. So before I start, I would like to thank my collaborators and supervisors, Philippe Faist and Jens Eisert, also my collaborators, Nicole and Jonas, who were there with me through this work. Also, I would like to thank the organizers for having me here. So before I exactly begin digging into the work which I have done, which is a part of my master's thesis, I would like to set in the prerequisites and the context. So here they are. So the first prerequisite is complexity. So what exactly does complexity mean? At the base of it, complexity is a measure of understanding how difficult is it to create a state or a unitary. So to understand this, we can just hop onto an example. Let's say I can create a unitary U using some using some R gates. Each of these gates is what we consider like simple gates which are given to us. So complexity here speaks of the smallest number of gates needed to construct this unitary U. Similarly, you can define it for states by optimizing over all the unitaries that take you from zero to that given state. Also, there are other interesting definitions of complexity. For example, there is one that Nielsen has discussed in his paper, which speaks of it as a length of a geodesic on some Riemannian manifold, and so on. There are several definitions of complexity, and all of them work for whatever we are going to speak today. That was the first prerequisite. And second one is thermodynamic erasure. So what we mean by that here is the fact that each reset of a qubit takes KTL into energy, takes at least KTL into energy. And it has been shown that protocols can be designed where it takes exactly KTL into energy. And this primitive we are going to consider, this reset we are going to consider as a black box or a primitive, and we won't discuss it much deeper than that. Now, setting up the context. So there have been several recent works trying to connect complexity to physics. For example, the paper by Brown and Susskind, which they call second law of complexity, where they hypothesize that there needs to be a second law of complexity, as in complexity should always be increasing or should be increasing with very high probability. And the second paper where they discuss complexity in the context of chaotic many body systems. Of course, the last paper here is from the same collaboration that I am in, where they show that in certain cases, the hypothesized second law of complexity indeed does exist. On the other side, you see the inspiration we have from resource theories, and our work tries to connect these two parts. We want to see how these two parts connect. That's for context. Now we can hop into what the problem statement of what I'm trying to do is, how we are going to deal with it, and why this way is kind of nice. So what? For example, consider you run a simulation of a black hole on a quantum computer. After you're done with the simulation, you need to reset the state. As a good guess, you take the measurement, you take the information out of the quantum computer, but you need to reset the state to return it to the people who come after you. So the question is, how difficult is it to reset? To understand this, let us isolate the problem. Consider an n-qubit pure state with high complexity. The mission is to get to state zero. I can do it in two ways. First way would be just pay the NKTL into energy, that is from the reset primitive that we have discussed before, or apply the uncompute operation U dagger to get back to the state zero, and we don't need to do anything else. So how I can visualize it would be like this. Given the amount of computational power you are given, you have to reset the state. If the computational power is zero, the best you can do is just reset all the states to the zero and pay the energy and move on. Or on the other extreme, when you have unlimited computational power, you can undo all the gates and not erase anything. This work addresses what happens if you have finite computational power, and we want to understand how this trade-off works. So how do we address this? So we address this using this quantity called hypothesis testing relative entropy, which was used in a previous presentation by Bartos. So what it does is basically this. It fixes it is about hypothesis testing between rho and sigma, as the name suggests. And we are doing the accepting and rejecting using these POVMs Q. So what we exactly do is fix the error of rejecting rho and optimizing the error of accepting sigma. This is how the picture looks like, or in words, the mission is to distinguish between rho and sigma, and we fix type 1 error to 1 minus eta and minimize the type 2 error. This has been like kind of discussed and characterized very well in this paper by Frederick Dupes and his collaborators. So why is this quantity interesting? So it can be connected to min and max relative entropies that were introduced by Nilanjana Datta in this paper. And there are several other relations with other entropies, which are greatly discussed in this paper as well. Though this quantity itself is interesting, it is way too complicated for us to use in this context. So we take a simplified entropy version of this quantity, which just looks like this. I will go into the definition again in the next slide. So yeah, that's how the entropic version of hypothesis testing relative entropy looks like. So now, if you look closely, we have a POVM effect Q, which can be split into a diagonal POVM effect and a unitary transformation. So we are one step closer to our solution. If we can restrict these unitary transformations, and if we can try to understand how the diagonal POVM should behave for our problem, we would solve the problem. So using that, we set up this complexity effective entropy. Oh God, apologies. The slides have become weird. But the thing I wanted to cut attention to is the restriction on Q. So in the complexity effective entropy, you have the restriction on the diagonal POVMs. You have a set of diagonal POVMs P, and you have the set of transformations U, which you can perform. So we can just discuss that now, which would like the set of unitary transformations which are allowed would be restricted by complexity, as that's the computational power we have. And an example for simplest set of measurements that we have P can look like this. It basically is we take projectors on some of the qubits, or we do nothing on the qubits. And such a set is a simple measurement. And we have the freedom of choosing that. So again, a revision of what we are doing. So the complexity effective entropy has a parameter for computational power, has a parameter for success rate, which is very, very closely related to the smoothing entropies that you see in various other entropic contexts. We have the state row and we have the set of simple measurements P. Why is this interesting? As we already said, it can relate to several other entropies, but we have some other properties which are cool as well. We have this thing about subadditivity, which is quite funky looking because we can only speak of, at the current understanding, we can only speak of separable states. And then we have the monotonicity in eta, which is quite obvious, and it is just inherited from the monotonicity of eta you have in hypothesis testing relative entropy. And the new monotonicity in R. Monotonicity in R is just stating that if I allow for more gates, I can get to a better optima, hence a better entropy. So that's there. By design, my entropy is not unitary invariant like other entropies. And yeah, that kind of fudges many other properties. For example, we instead of data processing inequality, we have a version of it which looks like that, but it isn't that. We can only speak of unitary processing. Here, R dash is the complexity of U. So that's that. And we can speak of asymptotic equivalence. It just it is kind of tautological, but since you can choose the set P, this is still an interesting property. So asymptotic equivalence just states that when I go to infinite complexity, all my complexity effective entropies converge to the hypothesis testing entropy. So now that I have set up the context and all the properties of the entropy we're working with, we can directly jump into the results. So I will be talking about a reset protocol and if the limits are achievable, and I can also show that these things are optimal. So task on the table again. I want to reset the state row to a state close to 0. The limitations I have, I can only use R gates from the gate set, and I can only use Landover primitives to reset. Of course, there are many kinds of protocols available, but I restrict myself to these kind of protocols where I apply the R complexity unitaries UR and then erase how many ever qubits I need to get epsilon close to the 0 state. In the circuit form, it would look like this. So the first result we have is about achievability. given a state rho, we can construct a protocol which has an R complex unitary, and the number of free sets is equal to the complexity effective entropy. I'll just give you the proof sketch now. So the mission is, as we have to construct a protocol which looks like this, and we start with the definition of complexity effective entropy. So we pick an optimal U and Q naught. By definition, U has complexity less than R. And for this example, Q naught might look like this. So very simply, that's how we can map these two things. There are, of course, some things under the hood I'm hiding, which is about translating the trace distance to fidelity distance and dealing with those, but it's not very important. It's just about understanding that Q naught tells us which qubits to erase, and the unitary that is optimal can be used as the unitary UR in our circuit, in our protocol. So similarly, I have a result of optimality where I can say that indeed this complexity effective entropy gives the optimal number of qubits that need to be reset. So we can put those together. Number of Landover parameters needed is approximately equal to hypothesis testing relative entropy. So we have the answer to the question we were asking. In this spectrum, the number of the work needed for resetting the system, given the computational power is R, would look like this. Now, yes, we have answered the question we were looking for, but we have some other interesting results too. So there was a measure of complexity which was called strong complexity, which defined by Brandau et al. In their paper, which I referred to earlier. We can use the similar construction to set up a strong complexity for mixed states, which has been kind of troublesome for various contexts. There have been discussions about understanding complexity for mixed states, where you can put it as a purification problem and then look at the complexity of the purified mixed state, purification of the mixed state. But we can address the strong complexity using our complexity effective entropy in this formulation. Also, we had some numerical, and we had some numerical understanding of how complexity growth works here, which I haven't included in these slides, but those are also some interesting results that can be discussed. Just jumping to the conclusion. So we established the trade-off between the computational power and work. And this trade-off is indeed quantified by the new entropy we have. And during this process, we understand the entropy and we can put in a complexity parameter, which is quite cool for all the applications that can be discussed in entropy. Of course, we adopted the formulation from Brandau to establish a strong complexity for mixed states. Of course, we also discuss the asymptotic behavior. So what next? So it is still not very clear to understand how much does the choice of the simplest set of measurements matters. And there is, in the vein of the paper with Jonas and collaborators, we want to understand how the complexity effective entropy grows under random gates. Simply speaking, do we see the similar growth with high probability in the context of complexity effective entropies? Of course, all the discussions that we have had is based on trivial Hamiltonian, where the state 0 and the state 1 have the same energies. But what happens in the other case? The good thing here is the framework we are using can be very easily adapted for that. So that would be an avenue we are trying to address. And as we said in the beginning, this work has been inspired from quantum chaos and the discussion of complexity in black holes too. So we want to see how it can be applied towards that. With that, I would like to thank you for having me here and listening to the talk. Yeah.
Thank you. This is really a very interesting talk, and it combines very interesting directions of research. I wonder if there's any question. I don't see any in the Slack channel and the chat. But so if you have any question, you can also unmute yourself and directly ask. Is there any question?
Yeah. Another thing I want to say is power and complexity in the discussion that we have are just placeholder terms. You can put anything in place of R. You can consider locality of the unitaries you're applying. You can speak of some other versions of complexity. For example, there was a version which we were discussing where you can talk of complexity as the band gap of the Hamiltonians that you're going through, and so on. So there are like the entire framework can accommodate for any version of complexity. It is agnostic to.
Yeah, this is a good note to add. Yeah. Sorry, I just noticed that there is a question on whether you could say more about how this is related to black hole in the chat. So can you say more about black hole versus this new?
So the point is this work was basically inspired from discussion of second laws of complexity by Susskind and Brown. So they try to understand the physics of it. So we want to see how we can connect that to the complexity of it. It's still not clear, and we are still trying to understand that part. It's the fact that we can take the complexity ideas that I discussed here to establish some understanding of how complexity and work can be related.
I see. Yeah, thanks for the answer. Okay, if there's no question, maybe I can ask one. So I'm wondering, let's say you defined the task of the erasure of quantum states with some complexity constrained unitaries, and you derive this trade-off as this new entropy. And I'm wondering how difficult it is, or how to compute this entropy, whether you already included or like what is the complexity of the complexity entropy? So how difficult it is to evaluate?
It is still quite difficult to compute. That is true. It is still difficult to compute, but there are some funny things you can do. Like for example, with the Nielsen complexity, you can set it up as a differential equation and compute the optimal unitary and then go on from there. But in other contexts, if we are considering the circuit complexity model, it is not very easy to compute.
I see. Yeah, thanks for the answer. Is there any more question? Still have a few minutes. Okay, if not, let's just thank the speaker and let us move on to the next talk. So, yeah.
Thank you for having me.